Okay, that's a carrot, and that's a UVVis spectrometer, similar size to an IR. We got a light source. IR provides IR light. UVVis provides ultraviolet and visible light. Two different types of light combined into a single spectroscopy. Okay? I thought everybody had one.
Please pass them back.
Okay, my slides are in color here. Okay, you need to review your electromagnetic spectrum. Okay, listed in terms of energy. This is the high energy in, gamma rays, X-rays, high energy in. Yeah. High energy and high frequency over here versus over here, low frequency, low energy. Okay. High energy, low energy. And of course, high energy goes with high frequency, and of course, high frequency would go with short wavelength. The short wavelength over here, long wavelength over here. So X-rays have higher frequency and energy than, say, radio waves, and X-rays have shorter wavelength than, say, radio waves, which have longer wavelength. So that's how that's shown. But you should know that already, right? And you know your different electromagnetic radiation, gamma, X-rays. UV visible combined into one spectroscopy we're covering here. IR, microwave, radio. Which has higher energy, IR or UV? UV. This way, UV, higher energy. Yes, it's the high energy UV from the sun which can cause damage. Okay, cancer. And X-rays would be even higher energy. And then gamma rays even higher. Which has longer wavelength, visible or IR? Okay, you see the trend. You need to know your trends there. When we use different radiation for, different types of light radiation, well, gamma rays we don't use. Gamma rays are found where, or I'm not that familiar with them, found in outer space. Maybe they're produced, I'm not sure. We don't use those for anything. X-rays used for medical imaging, okay, discovered about 125 years ago. Very important, particularly like during World War I when it was first really widely used. Medical imaging, but we can also do X-ray crystallography and get a diffraction pattern because molecules will deflect X-rays. And that can be miraculously turned into a structure based on how they reflect and deflect the X-rays. That was one of the ways that the structure of DNA was proven by X-ray crystallography. Okay, UVVis we'll be talking about today. IR we use to study molecules, gives us information about what? Functional groups, largely what type of bonds are there. Microwave, we can pop our popcorn, but we can also study the rotation of molecules. You're not going to see that at the undergraduate level. Radio waves, we can listen to our favorite radio station. We can also do NMR. NMR you'll learn in Organic 2 that uses radio waves. Okay? We don't use the term radio any, but it does use that type of radiation. Very weak and long wavelengths. Okay, here's an example UVVis spectrum of butadiene. 1,3 butadiene, but you really don't need the 1,3 because, well, you possibly could. There could be a 1,2. It would be accumulated diene. That's butadiene. We don't know nomenclature of dienes. And UVVis Here we got wavelength. And we got absorbance. And it looks pretty simple, particularly compared to an IR. IR has lots of peaks. And with IR, the peaks typically come down. Okay, lots of peaks, particularly in the fingerprint region. Here, typically, we got a peak up, absorbance. And this molecule is absorbing a lot of light here. High absorbance with wavelength of about 220 what? Nanometers. What do we say for UV invisible? UV is approximately 200 to 400 nanometers, visible 400 to 800 nanometers. Okay? Nanometer, what is that a unit of? Frequency, what? Wavelength. Wavelength, right? Okay. We're plotting wavelength. And visible has longer wavelength, right? Okay. What do we plot in IR?
On vibration.
What do we plot in IR? Those are the numbers. What are the units of those numbers? Inverse centimeters. So what is that? No, a centimeter is a length. It's inverse wavelength. It's a wavelength in centimeters, but it's the inverse. 1 over centimeter. Centimeter to the -1. Yeah. Why do we do an inverse? We don't do inverse in UVVis. Well, we can, instead of centimeters, we can convert to nanometers and make it a bigger number. Yeah. It's just some long ago, that's the way it was done, and that's the way it's done. Okay. The inverse was probably to make it a whole number. It's just, you know, after 100 years, 150 years, it has become the way it's done. But, you know, centimeter is a wavelength, and it's the inverse. And what do we call that number? It's called a wave number. Okay? A wave number. And the wave number, if you think about it, is actually the number of waves in the centimeter. Okay, so 200 to 400, 400 to 800, and here we go. You see, we're plotting here. 200 to, okay, it just stops here. The reason it stops is because there's no absorbance, and so this is just a flat line. But we can go out to 400 and then 400 to 800. But is there any absorbance out here? Apparently not. All the absorbance is where? Right here. Is this UV or visible? UV. That's UV, because visible doesn't start until 400 to 800. Okay? This compound will absorb a good amount of ultraviolet light. As we see here, we plotted good absorbance here. But it's not absorbing anything out here in the visible. Okay? Molecules will absorb. Molecules will absorb all types. Molecules will absorb X-rays, ultraviolet, they'll absorb visible, they'll absorb microwaves, they'll absorb radio waves. And we can graph that or plot it. Okay? What can we get here? The Lambda Max. Lambda Max is the wavelength of highest absorption. This is the highest absorption, right? Okay. This could be some type of arbitrary number, like 0 to 100 or 0 to 1. It's basically relative. This is the highest absorption, and it occurs where? Right here, which is about what? 217. About 217 nanometers. And that can become a physical constant for butadiene. The maximum absorbance is at 217 nanometers. Just like the boiling point is a physical constant, the density, the Lambda Max and the UVVis. Okay? If you think you got butadiene here, you could go run a UVVis, and what if we get a Lambda Max of 329? Does that sound like butadiene? No. We know butadiene has a Lambda Max of 217. Okay? Physical constant. Question, how do we get a peak? What's going on? Why does the molecule absorb the UV? We'll go back to IR. Why does a molecule absorb IR light? I'm sitting here minding my own business. I'm maybe a C oxygen double bond, carbonyl, minding my own business here. Somebody throws some IR at me. Ooh, I liked it. I absorbed it. And I go to a higher vibrational level. Okay? That's kind of what's going on. We only went halfway though. You know, we went from here to a higher vibrational level. We didn't ask how. How does the bond absorb? That's a lot of physics, and we've never said how. What we do, we are identifying some type of process though. Exciting bond vibration to a higher level bond vibration. So what's the process going on here when that molecule absorbs ultraviolet? There we go, carbonyl stretching. Throw me some UV. I just ignored you because I don't, okay, this has nothing to do with UV. Okay, I ignored you. Okay, throw me some IR. Ooh, I like that. Okay, UV, it does not belong here. So what happens, what leads to absorbance of UV? What happens? Yes. Ultimately, we excite an electron. Okay? Has nothing to do with a vibration or a bond. Okay? You can say, well, aren't electrons in bonds? Yeah. Ultimately, they've got an electron, throw me some UV. Bam, you excite me to a higher energy level. Okay? Electron excitation. Well, what type of electrons are possible? What type of electron transitions are possible? What type of electrons can be in a molecule? Sigma electrons? Those are electrons that are in sigma bonds. Pi electrons? Those are electrons that are in pi bonds. What other type do we have?
Lone pairs.
Lone pairs, or non-bonding electrons. That's three types. And that's three types shown here. Sigma, pi, non-bonding. These all have a certain energy level. But they can be excited to a higher energy level. And to understand these levels, you really have to have had some molecular orbital theory. Okay? Which I don't know that we've had much. But we have higher energy levels, and we can excite. Question, which one's easier to excite? Sigma, pi, or non-bonding? Don't even look up here. Which one do you think is easier to excite? Bonding electrons or non-bonding? Non-bonding. Non-bonding are easier to excite. Bonding electrons are held together and they're kind of more stabilized and they're held with that bonding glue. Non-bond lone pairs are easier to excite, so they take less energy to excite. If they take less energy, is that going to be, what type of light would do that? Long wavelength or short wavelength? Long wavelength. Longer wavelengths would be lower energy. What type of electrons are most difficult to excite? Sigma or pi? Sigma. Sigma's a stronger bond. They're held tighter right there, if you think about it simplistically. Sigma electrons, they're hardest to excite. What type of wavelength light do we need there? Shorter or longer?
Shorter wavelength, high frequency.
We need shorter wavelength, because that would be higher energy, right? Yes. You have to understand that type of thinking. Okay? Lower energy transitions are usually above 200 nanometers. UVVis starts about 200. Higher energy transitions, way higher, these can be below 200. Because below 200 is higher energy. Higher energy is needed to do higher energy transitions. Below 200 is called the vacuum UV. And we typically do not scan below 200. Back over here. See how we started? Oh, that's going the wrong way. See how we started at 200? Typically on these scans, we usually don't scan below 200. Does this compound absorb below 200?
A little bit.
It probably, we just cut it off there. Maybe it goes like this. And there's some absorbance below 200. Yeah. The reason we don't scan below 200 is because oxygen absorbs below 200. And if you scan down there, you're just going to get a big absorbance for oxygen. Now you could do a background. I'm not quite sure why a background can't easily be done like an IR can. Yeah.
When you say oxygen, is it like O2?
O2, yes. Oxygen. Oxygen. Oxygen's everywhere, right?
Right.
Okay. When you're running an IR, your sample's on the IR. Is there any oxygen around it?
Yes.
Yes. Well, guess what? When you run a background, you get rid of that. Because when you run a background, you run the instrument is run with nothing up there. Well, there's no compound up there. But what is up there around the eye of the IR eye when it's clean? Air. And what's in air? Oxygen, nitrogen, CO2. Okay? And all those things will give peaks in the IR. But when we do a background, we eliminate that. Because it takes the IR run with nothing up there. There's actually stuff up there. There's air up there. But it gives a spectrum of air, but it cancels that out from your spectrum. So when you do your spectrum of your compound, you don't get any peaks for oxygen, nitrogen, CO2. Okay? I'm not sure why you can't just do that here. Probably you can do it today, but in the olden days it was more difficult. It wasn't done. One way it was done in the olden days was to get rid of the air. How do you get rid of the air?
Vacuum.
Vacuum. So it had to be done under vacuum. And it became known as the vacuum UV range. The simple introductory instruments today just sort of start at 200 and go that way. Okay. Basically, transitions go to a ground state orbital to an excited state orbital. Excited state indicated with a star. We don't really have to know too much detail there unless you want to. Basically, electron excitations, different ones. The one that's going to require the most energy would be this one here. Biggest energy jump. That makes sense. Sigma electrons. Sigma electrons require the most energy to excite. Here's a UVVis spectrum of this molecule. Lambda max is what? Don't look over there. Right here? And it's about what? About 240. Okay, that's how the lambda max came up. Got a high absorbance there that kind of peaks out and it kind of fades up. It's almost like something else is going on here. Another little ridge. That's common. This has been ascribed to two different transitions. Pi electrons being excited and then non-bonding electrons being excited. The non-bonding electrons are being excited at a longer wavelength, like about 300. Does that make sense?
Yes.
Longer wavelength is lower energy. It took lower energy to excite the non-bonding electrons. Shorter wavelength is higher energy. It took higher energy to excite the pi electrons. Does this molecule have pi electrons? Yes. Does it have non-bonding electrons?
Yes.
Two lone pairs on the oxygen. This molecule also has sigma electrons, yeah? Where would the sigma electron excitation be? Even higher energy. Where would that be? Maybe over here in the vacuum UV, which we actually didn't scan. Okay? Does this compound seem to absorb in the visible? No. Visible starts 400 to 800. Apparently not. It's kind of coming and nothing out here. Wasn't even scanned.
Dr. Stevens,
Yes.
are the units on the y-axis still units of absorbance?
Do what?
Are the units on the y-axis still units of absorbance?
Essentially, they can vary. It looks like log. Yeah, you can see variations on how that's presented. Not important to us. Essentially, it's some type of absorbance. Different units, though. These slides come from different sources, so they're not going to be consistent in that regard. But it's not critical. Here is a UVVis of beta carotene. What do you see about that structure? Lots of double bonds conjugated. Have you counted them? Yes, it's 11 double bonds conjugated. Okay? 11, all conjugated. Here's the UVVis. Lambda Max is where? Right here? Maximum absorbance, which is what? About what? About 440 nanometers. Okay. What area do we call this?
Visible light?
UV vis. Lambda Max is in the visible. That is, beta carotene absorbs visible light. And it absorbs more visible than UV. Visible is the maximum absorbance. 440 to be precise. Before it was what, about 2 something? Why is this shifted more to the right? For a longer wavelength. Supporting question has to do with the conjugation. Okay? Also, what color is beta carotene?
Orange.
Very good, it's orange. Okay? Why is it orange?
Because it reflects orange light.
Do it?
It reflects orange light.
Yeah, but why? Tell me more. Why is it orange? Go back to butadiene. What color is butadiene, do you think?
No color.
It is a liquid. What color do you think it is?
Not visible.
Colorless? Why?
It doesn't.
How do you know that?
It doesn't absorb.
It reflects all light color.
There's no visible light that is absorbing.
Okay, for something to be colored, it has to absorb visible light.
And since
Okay? If it does not absorb visible light, it's going to be colorless. Or if it's a solid, it will be white. Because solids are typically opaque. Okay? Does butadiene absorb visible light? No, I don't see anything out here. Again, we keep going if there was anything out here to see. And so it should be colorless. Does that compound absorb any visible? Well, they kind of stopped it there. Doesn't seem to. How about this compound? Does it absorb visible?
yes.
Plenty. Plenty. Look, all this is visible that it's absorbing. Okay, it's going to be colored. That wall is blue because it's absorbing some visible light. Let's get it in. Let's look at it closer. Question.
Is it absorbing the higher energy?
We're going to look at it.
Oh.
We're going to look at it.
Did you predict what color your product?
Yes, yes, we're going to get there. Okay? Why is beta carotene orange and not green or yellow? Okay? We'll get there. First off, why is it shifted towards longer wavelengths? It has to do with conjugation. Okay? Here we go. Y'all familiar with LuMO and LuMO? Okay? I know you guys don't do much. When I took Gen Chem, we did plenty of MO and learned about HOMO. HOMO is highest occupied molecular orbital. Okay? Do molecular orbital theories, you get talking about different orbitals where electrons can sit. You're going to have one that's highest energy, not highest energy, but highest occupied. All these are occupied, but then you also have some that are not occupied. Those are called excited state orbitals. And they're not occupied until you excite something up to them. Okay. The highest occupied molecular orbital is called the HOMO. And the lowest of the unoccupied molecular orbitals is called the what? The LuMO, okay? All these are populated and all these are not, but there's a gap between the highest tier and the lowest tier. And typically when you do a transition, electron excitation, the first one is from here to here. We can excite from the HOMO to LuMO, okay? It turns out though, start here. One double bond, 2 conjugated, 3 conjugated, 4 conjugated. It turns out that as you increase conjugation, the gap between the HOMO and LuMO gets smaller and smaller and smaller. Thus, less energy is required to go from HOMO to LuMO. That's 4 double bonds. What if we have 11 conjugated? The gap between the HOMO and LuMO is going to get real small. And if it's real small, you don't need much energy to do the transition. And if you don't need much energy, what type of wavelength are you going to end up using? Longer and longer wavelength. Everything is quantized. You can't say I'm just going to stick with high energy and do that. No, it won't happen. You've got to use low energy to do a low energy transition. And so this is probably HOMO to LuMO. Again, there's many fine questions you could ask here. But the HOMO to LuMO transition is easier because of all the conjugation. Easier is going to shift your wavelength to longer, weaker light. Okay, you can read stuff there if I miss saying something. Okay, back to color. Why is beta carotene orange? Where's it absorbing at largely? 440? Okay. What color is 440?
Purple
Because within the visible, don't we have Roy G. Biv? Remember that?
and indigo.
Red, orange, yellow. By the way, which is red in? The 400 or the 800?
800.
Actually, 800 is the red. So it's Roy G. Biv going this way. So what is 400 light color?
Indigo and violet.
Biv, violet. Okay? Yes. Well, what color is 440? Well, we can look at a color wheel. 440 is, basically here's 800. You start at 800, Roy G. Biv, red, orange, yellow, Roy, green, G, blue, indigo, violet. Yeah? But 440 is pretty much blue. Beta carotene is absorbing blue light. So why is it orange?
You see the light that's reflected.
Because apparently if you remove blue light from white light, what are you left with? Orange. Yes. Okay. How do you know that? If you use a color wheel, if this is what it's absorbing, what will it reflect? The opposite. Okay? And if we go opposite of what it's absorbing, what do we get over there? You're going to be orange. Okay? What if the lambda, the lambda max, or the lot of absorbance is 780? What if lambda max is 780? High absorbance at 780 range. What color will it be? Green. Be green. Because you're absorbing a lot of red light, and you will thus be reflecting green. Okay? All right? This is why your handout needs to be in color, not black and white. Right? So, did we get it answered why beta carotene is orange?
Yes.
Why is that wall blue?
It reflects blue light.
Absorbs orange.
That wall is absorbing a lot of visible in here, maybe about 600 nanometers. There's some molecules in there that like to absorb about 600 and thus reflect what color? Blue. Right? Absorb here, go through the center. Okay. So if you want to create some color, you gotta have molecules that. All right. Rank in order from lowest, from highest to lambda max. Okay, what type of questions might you see? Standard type of question. Which would have the highest lambda max? Highest referring to wavelength position, not highest absorbance. A different lambda max. Or we could say lambda max of highest or longest wavelength. Okay. Which would have the highest lambda max?
The rise.
This one? 3 double bonds conjugated? Which will be next? Middle one, 2 double bonds conjugated? What will be the lowest? 2 double bonds not conjugated. Conjugation does what to the lambda max?
The wavelength.
Moves it to longer wavelength. And here that means higher. Okay? So I do have to be careful about this. Which compound in each set would have the highest lambda max? Remember the trans-stool beam and then the dibromide you made and then used last week? Which would have the highest lambda max? Here the double bond makes everything conjugated. All pi bonds are conjugated. When the double bond is removed by brominating it, these 2 rings are no longer conjugated. Completely conjugated molecule, no longer completely conjugated. This should have the highest lambda max. More conjugation. Lambda max moving to a longer wavelength. Diels-Alder reaction. This was maleic anhydride. This was the Diels-Alder product. Which would have the highest lambda max? With a double bond here, 3 double bonds conjugated. You can even argue lone pairs here. The double bond's no longer here. It's now over there after the 4+2 Diels-Alder. Now these 2 double bonds are no longer conjugated. And that's an isolated alkene. More conjugation here. Longer lambda max, longer lambda max.
Dr. Stevens,
Yes?
are we not considering the effects of lone pairs? Would lone pairs lead to a higher length?
Yeah, but if you're looking down here,
Or for the first one?
lone pairs no bromine, but they're not conjugated. Right?
However, in a few slides back, you also said that lone pairs require less energy to excite than ones that are in high bonds or single bonds.
I didn't make one statement back over here. Your lambda max typically comes from pi excitation. I didn't point this out here. Your pi to pi star transition, pi to pi excitation is usually the most intense. And thus it's usually the lambda max. Okay? We can go back over here and look here. Where is lambda max at? 240? Pi star. It's usually most intense. That's okay? Look here. Yes, it's more to the right. As you correctly said, non-binding electrons more to the right. Lower energy needed to excite them. But it's usually not the lambda max. All right? So the maximum absorbance usually comes from pi to pi star. Pi. And usually because of that, we kind of focus on talking about pi transition. Because it's the maximum absorbance. You've used UV in lab to look at your TLC plates. Okay. These plates have a dye on them. you look at the light, there's a short wave and long wave, 2 buttons. If you look at the label on the lamp, it'll actually tell you the nanometers for that. Short wave is usually, I think, about 270 nanometers, and long wave is, I think, more like about 320. Both being UV, but one shorter and one longer. Okay. And so have you guys used the longer light before and see if anything shows up? Because different compounds can absorb differently. That's what we're talking about here, different absorptions. We're moving through this quickly, guys. Some applications. You've used indicators, such as phenolphthalein. Colorless form. In the presence of base, it becomes magenta color. Why? Colorless means it's absorbing no visible. But now it's absorbing visible if it's colored. That means it's shifted. The Lambda Max is shifted to the right. Why? More conjugation. That's what will shift it. Does this molecule have more conjugation than that one? Yes. Look at this carbon. It's sp3, no p orbital. When this reaction takes place, the carbon is now sp2, and you have conjugation all the way through here. And the extended conjugation moves the Lambda Max to the right into the visible, and it becomes colored. This is pH dependent, and you can cycle back and forth between a colorless form and a colored form. And that can help you determine pH. We've got a couple of minutes. There's a question there. I'm not going to get at the difference in the Lambda Max. You can try to answer that if you want to kind of chew on that a little bit. A simpler question would be, which one is most likely pale yellow? One of these is white and one of these is pale yellow. Which one's pale yellow? You need to look at these numbers here. I gave you Lambda Maxes. Which one's most likely pale yellow? Why A? It's absorbing more to the right. Is it absorbing visible? No. That's Lambda Max. Okay? Again, just because Lambda Max is something like this here. Just because Lambda Max is over here doesn't mean it can't come out here and maybe absorb a little bit. Okay? I mean, what if this came over here and we had something that was right? It absorbed a little bit. Okay? Basically, the closer all this is to this, the more likely this is to spill into the visible region. And the one at the top is more to the right, and thus I think more likely to spill into the visible region. And if you just barely spill into the visible region, you start absorbing what color? Here? Just start absorbing, and if you absorb this, what color will you be? You'll be yellow. But will you be a deep yellow or a real pale yellow? If you're only absorbing a little bit, you're just going to have a little bit of color. Okay? Back when we had the Eclipse, I put this in. You got to be careful. Light, intense light coming into your eye. Okay? You can have problems. I'm not going to spend time on that. We just don't have enough time, guys. Fluorescence. You can read this. Okay, once a molecule absorbs, tell me some UV. Ooh, you excited me. Okay. Does that electron stay up there forever? No, it's going to come back down. When it comes back down, it releases energy. I absorb the energy. I'm going to eventually release it. How does it release it? A variety of ways. One way is to do this, fluoresce. When a molecule fluoresces, it releases back the light, but it doesn't release the same light it absorbed. Throw me some UV. Boom. I'm going to do this a little bit. I've gone down in energy. Now I'm going to give back out light. But the light I give back is in lower energy. And it can be low enough that it becomes not UV anymore, but it becomes what? Visible. That's what's happening here. Quinine will absorb UV and then give back off visible. This is an absorbance spectrum, but this is what it gives back off. It absorbs UV and it gives back off visible. But it largely gives off blue light. If you shine UV on quinine, which is in tonic water, it will throw you blue light back at you. This is the idea of fluorescence. Sometimes you see in biology, this is a sea creature getting UV from the sun, but then throwing back out pink light. Okay? Fascinating. We don't have enough time. You can read about it. What was at the end here? There was one more handout, sunglasses that turn dark. Did you get that in your handout?
Yes.
Okay. Yeah, basically some sunglasses can have molecules. Okay. Lots of applications. We just don't have enough time, guys. Have a good break. Be safe. Test on Monday. I'll post the video key.